We had started talking about it in the last class. What is the meaning of two sound waves interfering? It means the same set of particles are subjected to two different sets of disturbances. And the particles in the medium are now going to vibrate according to how these two disturbances superimpose on each other. Is that right? Do you remember? If this is a particle in a medium, and if two waves are superimposing on this particle, the vibration of this particle will depend on how they superimpose. If the two waves are in phase, what does that mean? If the compression of one wave falls on the compression of the other wave, that means this particle will have maximum displacement. You have a much bigger wave. That means the waves are in phase. So when two waves meet in phase at a particular point, you get a much bigger wave. In the case of sound, it means when two sound waves meet in phase at a point, you hear a loud sound. Whereas if they meet completely out of phase, you hear no sound, because the displacement caused by one wave will be cancelled by the displacement caused by the other wave. A particle which is vibrating back and forth will not vibrate. So, one more time, let me repeat. If two waves meeting at a point are in phase, both the waves will make the particles vibrate in the same sense. The particle will vibrate with much larger amplitude and you hear a loud sound. Whereas, if two waves meeting at a point are completely out of phase, you hear no sound. Okay. Two sound waves advancing in the same medium will generate two separate displacements on the same set of particles. I hope that concept is clear now. If the two waves are in phase, these displacements will add up, producing a larger displacement, like this. Now, I told you I will use the crest and trough method to represent a compression and rarefaction. The compression of one wave falls on the compression of the other. The rarefaction of one wave falls on the rarefaction of the other. That means the waves are in phase. You get a much bigger wave and therefore a much louder sound. So, since the loudness of a sound produced depends on the square of the amplitude, this will generate a much louder sound. If the two displacements are out of phase, what will happen? The displacements they produce on the particles of the medium will cancel each other and the resultant wave will have no amplitude. If the resultant wave has no amplitude, it means there will be no sound. Alright, now the compression of one wave falls on the rarefaction of the other wave. You see that? That means the displacements produced on the particles are completely opposite. They will cancel each other. There will be no wave. Now, I have an animation here where one wave advancing from the left superimposed with another wave advancing from the right. You can see where they meet in phase. You can see where they meet in phase, you got a bigger wave. Where you see darker regions are where they meet in phase. Where you see lighter regions are they meet completely out of phase. So as they move, as the two waves move towards each other, in some regions they are completely in phase. In some other regions they are completely out of phase. And this situation keeps repeating. And that is a phenomenon actually very interesting. Alright. Now, one more illustration there. This is a case of constructive interference. What's the meaning of constructive interference? when the two waves are in phase, they add up to produce a much bigger wave. There you are. On the other hand, if the two waves are completely out of phase, the compression of one wave falls on the rarefaction of the other, you have destructive interference there. So, constructive interference, destructive interference. I have another illustration here. Let me tell you what this is. Suppose you have two loudspeakers at two different points in a room. Here S1 and S2 represent two loudspeakers, and sound is coming from both. That means if you now walk from one end of the room to the other, at certain points sound coming from S1 and sound coming from S2 will be in phase. You will hear a loud sound. But as you move a little later, you will see sound coming from S1 and sound coming from S2 will be out of phase. You hear no sound. So, a very interesting phenomenon. If you move from left to right, you will hear at some points loud sound, at some other points no sound. You can actually make it out. But in actual practice, I know most of you will tell me, oh, I have two loudspeakers in my room, but if I walk around in my room, I can hear the music very well everywhere. Well, yes, you know why? Because the music you hear is not only the direct sound coming from the loudspeakers, but also the sound that gets reflected from all over the room. That's why you're able to hear. If there are no reflections, if you hear only the sound coming from the loudspeaker, if you walk from one end of the room to the other, there will be places where you hear loud sound, and there will be places where you hear no sound. Now, this is very clearly illustrated here, where they meet in phase and completely out of phase. Now, at A, I have tried to mark those. You see, they are out of phase, in phase. Well, by the time I point, it changes already. So out of phase, in phase, out of phase, and so on. I have tried to mark some points in there. You see that? They are out of phase, they are in phase, they are out of phase, they are in phase, and so on. Well, try and do this experiment. Sometimes you might succeed. Alright, so along the red lines, the compression of the wave from S1 falls on the compression of the wave, see that? Over here. There you are. There you get constructive interference. And along the green lines, there you got, along the green lines, they meet completely out of phase, producing no sound. So when you walk from left to right, if you come to the red line, you hear loud sound. Come to the green line, you get no sound, loud sound, no sound, and so on. Alright, let's leave this and move on. One more illustration. Now, this represents the sound waves coming from speaker 1, and this represents the sound waves coming from speaker 2. You notice that the crest of the first wave and the crest of the second wave are together. So this is a case where the two sound waves are in phase. Is that right? They are in phase, therefore you have a much bigger wave. You hear a loud sound. On the other hand, look at this. Now watch my little iron rod again. The crest of one, remember when I said crest, it stands for compression. The compression of the wave coming from speaker 1 falls on the rarefaction of the sound coming from speaker 2. What happens here? They are completely out of phase, therefore there is no wave. The amplitude is 0, you hear no sound. I hope the concept of interference is clear now. Okay, let's move on. And here is an animation of that. You see one wave and another wave. But they are not really the same. If you watch them, they are not similar, because as wave on the top advances and the wave at the bottom also advances to the right, they can't, you see that they are now in phase. You've got a big wave. Now, soon they are going to get out of phase. No wave. Watch these particles here. They are now in phase. There's maximum displacement. Now they are out of phase. There's no displacement. Take some time to watch it. And watch just these two particles and watch how these two waves interfere. They are now going to be in phase, you see, maximum displacement. And now soon they will be out of phase, no displacement. And this situation will keep on repeating. Very interesting situation. Alright? Okay, let's move on. Let's now talk about phase difference and path difference. I hope you remember the concept of phase difference that we talked about. Well, what is the phase of a particle? A particle vibrating, well, if you talk about the longitudinal wave, equilibrium, right extreme, back to the equilibrium, left extreme, back to the equilibrium. Now, phase angle tells you where the particle is at a given time. If the phase angle is 0 at the origin, the phase angle is pi by 2 at the right extreme. The phase angle is pi when it comes back to the origin. The phase angle is 3 pi by 2 at the left extreme. And the phase angle is 2 pi back at the equilibrium position. That means at the equilibrium position, the phase can be 0, pi, or 2 pi. If the phase is 0, means it is beginning to vibrate. The phase is pi, means it has completed half a vibration. If the phase is 2 pi, means it has completed one full vibration and is going to start again. Alright? Okay, so phase difference and path difference. What is the path difference? I think we need to construct that concept now. Let's now talk about this. Suppose this is waves coming from loudspeaker 1. And here is loudspeaker 2. And you are sitting here. You see? Waves coming from loudspeaker 1 and waves coming from loudspeaker 2 reach point C where you are sitting. The path difference. What is the meaning of path difference? A path stands for length of the path. This is the length of the path taken by waves from here. And this is the path taken by waves from here. So path difference is the length BC minus the length AC. That is what we call the path difference. Now, we're going to now discuss how is the path difference related to phase difference. One wave starts from point A, another wave starts from point B. How do we know if they are in phase or out of phase when they meet at C? How do we know? How do we know that these two waves meet at C in phase or out of phase? Well, when a wave propagates in a medium, particles of the medium in intervals of one wavelength are in the same phase of vibration. Well, that means if one particle has completed one vibration, it is now beginning to start a new vibration. So, if now you got another particle also starting, then these particles are in the same phase of vibration. That means if this particle has completed 5 vibrations and another particle here has completed 10 vibrations, they are both starting a new vibration. They are in phase. You understand that? So when a wave propagates in a medium, particles of the medium in intervals of one wavelength are in the same phase of vibration. What does that mean? Intervals of one wavelength. You see, the distance advanced by the wave for one complete vibration is what we call one wavelength. So, if the difference between this distance is one wavelength, that means by the time the energy reaches here from A and the energy reaches here from B, they will be in phase, because the difference is one wavelength. Difference is one wavelength means one complete vibration. You are now beginning a new vibration. So the energy from here and the energy from here will be in phase. How about if the difference between the two parts is two wavelengths? Well, then again they will be in phase. In other words, if the path difference is an integer multiple of the wavelength, then they will be in phase. Alright, if there are 50 Hall waves in the distance AC, and there are 44 Hall waves in the distance BC, then the waves from A and waves from B will be starting a new wave at C. That means they arrive in phase. I hope you understand that concept. If the difference between the paths taken by the two waves to reach C differs by an integer multiple of the wavelength, the difference can be one wavelength, two wavelength, three wavelength, four wavelengths, and so on. They will meet in phase. For any integer n, the condition for two waves to meet in phase, what is the condition? That the difference between the length of their paths must be an integer multiple of the wavelength. The path difference equal to n lambda, where n is an integer. It can be 1, 2, 3, 4, 5, 6, and so on. Then constructive interference will happen. So once again, the condition for constructive interference to happen at C is that the path difference between waves coming from the two sources must be an integer multiple of the wavelength. In that case, tell me, when will the destructive interference occur? Destructive interference occur if when one particle completes half a vibration due to one wave, the second wave is coming to start a new vibration. That means they will be completely out of phase. In other words, a phase difference of pi. A phase difference of pi means the particle has completed half a vibration. Half a vibration, how much is the energy advanced? Half a wavelength. That means if the difference between the path from A and B is half of a wavelength, then when they arrive in C, they are going to produce displacements completely opposite of each other. They are destructive. You get destructive interference. That means the condition for destructive interference is that the path difference must be an odd multiple of half of a wavelength. You see, you cannot have even multiple of a half wavelength, because even multiple of one half will be an integer multiple. So you got to take odd multiple of half of a wavelength. And how do we write it? So for destructive interference, the path difference must be, look at the way I construct what is called an odd number, 2n plus 1. You put in any value for n. N equal to 0 gives me 1 lambda by 2. N equal to 1 will give me 3 lambda by 2. N equal to 2 will give me 5 lambda by 2. So this gives you an odd multiple of half a wavelength. So the condition for destructive interference is that the path difference must be an odd multiple of half a wavelength. Now, do you understand this? That the path difference of lambda is equivalent to the phase difference of 2 pi. I have explained that to you. By the time a particle completes one vibration, that means it has gone through 2 pi radians, the wave has advanced by 1 wavelength. So a path difference of 1 wavelength is the same as a phase difference of 2 pi. In that case, tell me, a phase difference of pi is equivalent to a path difference of what? Will be lambda by 2. Is that right? Yes. Okay. If there are 6 whole wavelengths in the distance AC and 6.5 wavelengths in the distance BC, when the wave from A starts a new wave at C, the wave from B has already set the particle halfway through vibration. That means they are completely out of phase, and therefore the displacement on this particle due to wave from A will be opposite to that due to wave from B. They cancel each other. There will be no wave at C. So a phase difference of pi is the same as the path difference of lambda by 2. I hope you understand that. We will now be able to equate the phase difference to path difference. So let's review that. A phase difference of 2 pi is the same as the path difference of lambda. A phase difference of pi is equivalent to a path difference of lambda by 2. A phase difference of pi by 2 is equivalent to a path difference of lambda by 4. Is that right? Okay, let's go on. A phase difference of pi by 2 is the same as the path difference of lambda by 4. Let's do a small problem. 2 sounds of the same frequency, 170 Hertz, are produced at points A and B. So the frequencies of the sound produced at points A and B are the same, 170 Hertz. What are the path difference and the corresponding phase difference for waves reaching at C if C is 10 meters from A and 14 meters from B? Well, we have 3 situations. Let's take one at a time. First of all, we know that the frequency of the sound is 170 Hertz. The amplitude of vibration is 0.025 meter. Well, we don't need to worry about that. The speed of sound is 340 meters per second, and so on. First, we find the wavelength lambda. Is that right? We need to find the wavelength lambda. Now, how do we find the wavelength lambda? If you know the frequency of the sound, we know the speed of sound. You know, I haven't given it to you there, but I have told you, whenever you need the speed of sound at room temperature, use it as 340 meters per second. Well, tell me, if you know V and F, how do we find lambda? Lambda equal to V over F, and that will be 340 meters per second divided by 170 Hertz, that is 2 meters. So lambda equal to 2 meters. Okay, now we are ready to do this. Well, C is 10 meters from A and 14 meters from B. Tell me, what is the path difference between waves coming from A and waves coming from B? Well, the path difference between waves coming from A and B in case A will be 14 minus 10, which is 4 meters. And 4 meters is 2 wavelengths. Is that right? Because we calculated the wavelength to be 2 meters. Because the wavelength is 2 meters, the path difference 4 meters is equivalent to 2 wavelengths. Tell me, are the waves from A and B meeting in phase or out of phase? They will be meeting in phase. Therefore, what will be the resultant amplitude? The resultant amplitude will be double the amplitude, which will be double that of 0.025. So the phase difference is 0. Alright, let's do B. 10 meters from A and 11 meters from B. Alright, tell me, what is the path difference between those two waves? 10 meters from A and 11 meters from B. The path difference is 11 minus 10, which is 1 meter. Well, a path difference of 1 meter is how many wavelengths? Our wavelength we calculated is lambda equal to 2 meters. So this is half of a wavelength. That means the path difference between waves arriving from A and B at C is half of a wavelength. They are meeting completely out of phase. So these are completely out of phase. Therefore, the phase difference will be pi. A path difference of lambda by 2 is the same as the phase difference of pi. Alright, let's do C. 10 meters from A and 10.5 meters from B. What is the path difference of waves coming from these 2 points? It will be 10.5 minus 10 is 0.5 meter. Tell me, what is this in terms of the wavelength? The wavelength is 2 meters. Therefore, 0.5 meter is a quarter of a wavelength. Alright, now you tell me, what is the phase difference that corresponds to a path difference of lambda by 4? Alright, that will be pi by 2. Okay, so you must be able to do problems of this type. Let's do another one. 2 sound waves oscillate in phase with a frequency of 100 Hz. At a 0.5 meter from one source and 5.85 meter from the other source, the amplitude from each source separately is A. What is the phase difference between the waves from the 2 sources at this point? Do you understand the question? Well, you see, if you don't understand the question, you cannot do it. So read it and see whether you can understand it and pick the data given. The frequency of the sound is 100 Hz. And of course, this is sound. The speed of sound at room temperature is 340 meters per second, which will help us to find the wavelength, right? Alright, so wavelength is V over lambda is 340 divided by 100 is 3.4 meter. Now, at a 0.5 meter from one source and 5.85 meter from the other source. So, what is the path difference between the 2 waves? The distance of one source is 5.85, the other source is 5 meter. That means the path difference is 5.85 minus 5, which is 0.85 meter. Alright, tell me, this 0.85 meter is what part of the wavelength? Wavelength is 3.4 meter. So can you write this path difference in terms of the wavelength? Yes, I got it as lambda by 4. Isn't 0.85 1/4 of 3.4? So the wavelength is lambda by 4. Now what does this wave, the path difference is lambda by 4. What does this path difference correspond to in terms of the phase? It corresponds to a phase difference of pi by 2. So at the point C, when they meet, they have a path difference of lambda by 4 or a phase difference of pi by 2. Another problem. 2 loudspeakers are separated by a distance of 6 meters. A listener sits directly in front of one speaker and at a distance of 8 meters, so that the 2 speakers are the 2 speakers and the listener form a right triangle. Find the lowest frequencies for which the path difference from the speakers to the listener will be an odd multiple of 1/2 wavelength. In other words, we want to find the path difference for which the waves from both speakers will meet completely out of phase. Okay, let's draw a picture. There are the two speakers, and here is the listener. Alright, this speaker is 8 meters from the listener, this speaker is 10 meters from the listener, and the speakers are 6 meters apart. You got a right triangle. Well, actually all this information was not given. You are given that the two speakers are separated by 6 meters, and one speaker is 8 meters from one speaker. The listener is 8 meters from one speaker. Therefore, what is the distance of the listener from the other speaker? That is the hypotenuse there. If this is 6 and that is 8, this must be 10, because 6 squared plus 8 squared equal to 10 squared. Alright, the path difference of the waves reaching the listener from the two speakers. What is the path difference of the waves reaching the listener from the two speakers now? It is 10 minus 8, 2 meters. And what is the wavelength of this wave? We don't know, is that right? We said when the path difference is an odd multiple of lambda by 2, what do we have? 2n plus 1 multiplied by lambda by 2. You see, this is the way we say that the path difference is an odd multiple of lambda by 2. We got to find that condition. So we're going to say this path difference of 2 meters is an odd integer multiple of the wavelength. We say it's 2n plus 1 times lambda by 2 equal to 2. Now, what is the smallest value of n? We are supposed to find the lowest frequencies. Now, the lowest frequency occurs when n, the integer, has the lowest value. What's the lowest value of n? Well, the lowest value of n is 0. You see, when n equal to 0, you got lambda by 2 equal to 2. Is that right? So the lowest frequencies correspond to n equal to 0 and n equal to 1. And when n equal to 0, we got lambda by 2 equal to 2, or lambda equal to 4 meters. So the wavelength of the lowest frequency is 4 meters. Therefore, what is the frequency of that sound? F equal to V over lambda. V is 340 meters per second, and lambda is 4 meters. So the lowest frequency that satisfies that condition, this condition, that is, the path difference is an odd integer multiple of the wavelength, is 85 Hertz. So when the frequency is 85 Hertz, the waves from both speakers will cancel each other. There will be no sound there. What is the next higher frequency which will do the same thing? That happens when n equal to 1. And when n equal to 1, 2n plus 1 will be 3. This will be 3 lambda by 2 equal to 2. Or what is lambda equal to? Can you solve lambda from here? Lambda will be 4 over 3 meters. So lambda equal to 4 over 3 meters. What is the corresponding frequency? The corresponding frequency is V over lambda, and that will be 255 Hertz. The two lowest frequencies for which the waves will arrive completely out of phase, producing no sound. Alright. Now, why can these frequencies be heard even if the speakers are driven in phase by the same amplifier? But does it mean that these frequencies cannot be heard? Well, actually those frequencies can be heard. Why? Because, as I told you earlier, the sound you hear is not only the direct sound from the speakers, but also the sound that is reflected by the walls and the ceiling And therefore, you can actually hear all the frequencies that are coming from the speakers. Although, some of these frequencies will satisfy the condition for destructive interference. Alright, okay, let's move on and talk about another important concept. And that's called beats. Beats. A very, very interesting phenomenon. You see, what happens when you send out two sounds at the same time in the same medium of slightly different frequency? When you say slightly different frequency, we are saying slightly different wavelength. I have a picture here, a blue wave. I don't know whether in the picture you can see the difference between blue and red. I have been seeing the camera is not very sensitive to red. I have a red wave that I'm pointing and a blue wave. Actually, they are of slightly different frequency. That means they have slightly different wavelength. That means if they start out in phase, after some time they will be completely out of phase. See that here? The red wave, the compression is falling on the rarefaction of the blue wave. Here they are completely out of phase. But as they advance, because of the difference in the wavelength, as they advance, they get in phase a little later. Look at that. They are completely in phase here. But a little while later, they get out of phase. You see it here? Here the compression falls on the rarefaction. But a little later, they get in phase. The compression falls on the compression. The rarefaction falls on the rarefaction. You get a loud sound. So what would you expect to hear in such a case? When two sounds of very nearly equal frequency are produced together, as they advance in the medium, they get in phase. There you are. They get in phase, out of phase, in phase, out of phase continuously. What does that mean to you? You will hear a loud sound, no sound, loud sound, no sound, and so on. Now, this is what we call the beats. And the number of times you hear loud and no sound is called the beat frequency. Now, what does the beat frequency depend on? The beat frequency depends on the difference between the two frequencies. Now remember, if the two frequencies are exactly the same, then they start out in phase, they will be in phase every time. Is that right? Now this phenomenon occurs because of a small difference in the frequency. The number of times they get in phase and out of phase. The number of times they get in phase, out of phase, in phase, out of phase per second is the difference between the two frequencies. Alright. So, the figure shows two sound waves, one with a frequency of 10 Hz and the other with a frequency of 12 Hz. That means there is a small difference in the frequency, that is 2 Hz. So, as they advance, these two waves will get in phase and out of phase 2 times a second. They have the same amplitude, but they differ slightly in the frequency and wavelength. So if they start out together, they will be in phase, producing a loud sound, constructive interference. And that's what you see when they interfere constructively here, you get a loud sound. But soon they get out of phase, you get no sound. And then a little later they get in phase, you get a loud sound. So, a sound of frequency 12 Hz, another of 10 Hz, advancing together, will get in phase and out of phase how many times a second? 2 times a second, producing 2 loud sounds and 2 low sounds. Alright, So as they advance, they gradually get out of phase and the phase difference between them will increase. At some point, they will be completely out of phase and there will be no sound. Alright? And then, as they advance again, they get in phase, you get a loud sound. And here is an illustration, the same illustration I showed you earlier. These two waves have slightly different frequencies. So as they advance, they get in phase, out of phase. If you stand here, see, now you hear a loud sound, and now you hear a no sound, now hear a loud sound. You keep hearing loud sound, no sound. That means at a particular point, they get in phase. There you are. Now they are out of phase. Now they are in phase. If you watch quickly, you get loud sound, no sound, and so on. And this phenomenon is what we call beats. The waxing and waning of sound as two sound waves of nearly the same frequency advance together in a medium is called beats. Well, let me see if I can produce beats for you. Well, I don't know if it's going to record well. I'm going to try. Well, I have two tuning forks here. Well, it's difficult for me to show. I have two tuning forks here. What I can do is, in the case of this tuning fork, I can adjust the frequency by moving this weight up and down. The frequency of vibration can be changed. Now, I'm going to sound these two together. Alright? Let's see. You got to believe me, because I'm going to keep them right here where you cannot see. The camera cannot actually look down. I'm going to sound them together and listen to this. That's one sound. Do you see the sound going up and down? Or do you hear? Well, I think I can hear. I'll try one more time. Isn't that beautiful? That's beats. Now, let's see if I can change the beat frequency. How do I change the beat frequency? By changing the difference between the frequency. I'm going to move that sliding weight a little and see whether you notice any difference. Do you hear the sound going rapidly? That's right. One more time. I think it's very clear. But if you tell me that you cannot hear it, that will be a misfortune. That's right. Yes. So two waves of very nearly equal frequency are advancing together. They are getting in phase and out of phase continuously, producing beats. Okay, let's move on. The number of beats heard per second is equal to the difference between the frequencies. Alright, let's move on. Let's do a simple problem. Two tuning forks have frequencies of 256 Hz and 260 Hz. Now this is a big problem. Is that right? Alright, if the forks are vibrating at the same time, what is the beat frequency? You might ask me, why did you waste your time on this problem? Well, just for the sake of it. What is the beat frequency? Beat frequency is the difference between the frequencies there, which is 4. Well, I took it away quickly. Another one. When a violin string is played without fingering, well, you know a violin is played by adjusting the length by using your fingers, is that right? Okay. When a violin string is played without fingering simultaneously with a tuning fork of frequency 480 Hz, beats are heard at the rate of 4 beats per second. When the tension in the string is increased slightly, the beat frequency decreases. what was the initial frequency of the violin string? Well, the beat frequency is 4 means that the difference between the frequency of the tuning fork and the frequency of the violin string is 4. But we don't know which is greater. We only know that the difference is 4. So this means that the frequency of the violin string can be 476. That is 4 less than the frequency of the tuning fork, or 4 more than the tuning fork, that is 484. We got to decide which is the correct frequency. Now, so the frequency of the tuning fork is 480. The frequency of the violin can be therefore 476 or 484. Now, what did we do? When the tension on the string is increased, tell me, if the tension is increased, is the frequency going to increase or decrease? You must know that. When the tension is increased, the frequency is going to increase. In other words, the frequency of the violin string is slightly increased, which means if it is 476, it's going to be closer than 480. If it is 484, it's going to go that way. It's going to go away from 480. That means if it is 476, when the tension is increased, if the frequency of the violin string is this, then the frequency, when the frequency is increased, the beat frequency must decrease. On the other hand, if this is the actual frequency of the violin string, then an increase in the tension should result in an increase in the beat frequency. Now, what happened actually? When the frequency of the string is increased, the beat frequency is found to decrease. Therefore, tell me which of these values is the actual frequency of the violin string. Well, this is the frequency of the violin string, because from 476 you increased it slightly, then the beat frequency decreases. So this is the value of the frequency of the violin string and not this. So the frequency of the violin string is 476 Hertz. Well, what I'm going to do is to stop this lesson here. I'm going to continue this lesson a little later, a second part for this lesson. There are a couple of important concepts I want you to learn. Alright, so you're not ready for test 1 yet. That will be after the second part of this lesson. Alright, I will see you later for that part.